Derivatives are fundamental in calculus, machine learning, and understanding how things change. Let's explore them through three lenses: formal mathematics, real-world examples, and simple analogies explanations. Let's start with the formal mathematical definition of a derivative. The derivative of a function at a point gives the slope of the tangent line at that point. It measures how sensitive the output is to small changes in input. The derivative f prime of x is defined as the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. Let's visualize this with an example function f of x equals x squared. At any point on this curve, we can draw a tangent line representing the instantaneous rate of change. Let's pick a point at x equals 1.5. Now let's compute the derivative step by step. First, we evaluate f of x plus h, which expands to x squared plus 2xh plus h squared. Subtracting f of x gives us 2xh plus h squared. Dividing by h leaves 2x plus h. Taking the limit as h approaches 0, we're left with 2x. Therefore, the derivative of x squared is 2x. Let's understand derivatives through a real-world example of a moving car. Imagine you're driving a car where your distance traveled follows time squared. Your speedometer shows your derivative, how fast you are going at each moment. As you accelerate, the speed increases steadily, just like the derivative 2x suggests. Let's see this mathematically. The position function shows distance equals time squared. Its derivative, the speed function, shows speed equals 2 times time. This demonstrates a key concept. The derivative of position is speed. When distance follows time squared, speed increases linearly with time. Let's make this even simpler with an example, going down a playground slide. Imagine a child sliding down. At the steep part, they accelerate quickly. This is like a big derivative. At the bottom where the slide flattens out, they slow down. This is like a zero derivative. This shows how derivatives measure how quickly things are changing at any point. Now let's explore the first derivative in more depth. The first derivative tells us about the slope and behavior of a function. Consider this cubic function. Its derivative is a quadratic function that tells us where the original function is increasing or decreasing. The derivative function shows positive values where the original function increases, and negative where it decreases. The points where the derivative equals 0 are called critical points. These mark where the function changes from increasing to decreasing or vice versa. The green regions show where the derivative is positive and the function increases. The red regions show where it decreases. In summary, when f prime of x is greater than 0, the function increases. When less than 0, it decreases. Critical points occur where f prime equals 0. Let's understand this with a real-world analogy: hiking up and down a mountain trail. Imagine this curve represents your altitude as you hike. The steeper paths represent greater derivatives. As you climb uphill, that's a positive derivative. Going downhill means negative derivative. Flat spots are where the derivative is 0. The altitude graph shows your position over time. Its derivative shows your climbing speed, positive when ascending, negative when descending. This demonstrates how the first derivative represents rates of change in real-world situations. For children, we can explain derivatives using a ball rolling down a slide. Watch how the ball speeds up on steep sections and slows down on flat paths. The derivative tells us how fast the ball is moving at each point. Big derivative means fast movement. Small derivative means slow. Now let's examine the second derivative, which tells us about a function's curvature and acceleration. A positive second derivative means the function is concave up, like a bowl. Negative means concave down, like a hill. When the second derivative changes sign, we get an inflection point where the curvature changes. The second derivative test helps identify maxima and minima. If f prime is 0 and f double prime is positive, we have a local minimum. If f prime is 0 and f double prime is negative, it's a local maximum. When f double prime is 0, we may have an inflection point. In driving terms, the second derivative represents acceleration, how your speed changes over time. Imagine this car's speedometer shows your first derivative, while the acceleration shows your second derivative. When you press the gas pedal, you experience positive acceleration. When braking, negative acceleration. The second derivative captures these changes. This demonstrates how the second derivative represents the rate of change of the rate of change. Acceleration in physics terms. Children can understand second derivatives through the exciting example of a roller coaster ride. The ups and downs create changing forces. When the track curves upward, you feel pushed into your seat. When it curves down, your stomach drops. These changing forces correspond to the second derivative. The first derivative is your speed, but the second derivative is what makes the ride exciting. Let's explore partial derivatives, which are essential for understanding functions with multiple variables. Consider a function f. X, y, equals x squared plus y squared. We'll visualize slices of this function to understand partial derivatives. First, let's fix y equals 1 and look at f. X, 1, equals x squared plus 1. This gives us a parabola. The slope of this tangent line is the partial derivative with respect to x, which is 2x. At x equals 1. This equals 2. Now let's fix x equals 1 and look at f. 1, y, equals 1 plus y squared. This gives us another parabola. The slope here is the partial derivative with respect to y, which is 2y. At y equals 1, this also equals 2. These partial derivatives tell us how the function changes when we vary just one variable while holding others constant. Let's understand this with a real-world analogy of a hiker on a hill. Imagine a hiker standing on a hillside. The steepness depends on which direction they face. Facing east, the slope might be gentle. This is like a small partial derivative with respect to x. Facing north, the slope might be steeper. This is like a larger partial derivative with respect to y. The hiker's experience changes based on direction, just like partial derivatives measure slope in specific directions. For a simple example, imagine a playground slide with different slopes on each side. One side is steep, This is like a large partial derivative. The other side is gentle, a small partial derivative. A ball rolls slowly down the gentle side, but quickly down the steep side, just like how functions change at different rates in different directions. Partial derivatives help us understand these different rates of change in each direction. Let's explore higher-order derivatives and their fascinating patterns. Consider the sine function. Its first derivative is cosine, representing how the sine function changes at each point. The second derivative brings us back to negative sine, showing how the rate of change itself is changing. This represents acceleration in physical terms. The third derivative gives us negative cosine, known as jerk in physics, measuring how acceleration changes over time. Remarkably, the fourth derivative completes the cycle, bringing us back to the original sine function. This pattern continues infinitely. Each derivative has special names in physics. Velocity for first, acceleration for second, jerk for third, and snap for fourth derivatives. In machine learning, derivatives power optimization algorithms. Gradient descent uses first derivatives to find minimums, while Newton's method uses second derivatives for faster convergence. Derivatives are truly everywhere in our world, connecting mathematics with physics, engineering, economics, and modern AI. They describe the slope of curves in mathematics, forming the foundation of calculus. In physics, derivatives model motion through velocity and acceleration. Modern machine learning uses derivatives to optimize neural networks through gradient descent. Economists use derivatives to analyze marginal costs and revenues in business decisions. Engineers rely on derivatives to understand rates of change in everything from electrical circuits to structural designs. This universal language of change helps us model and predict how systems evolve, making derivatives one of mathematics' most powerful tools. I hope you found this video helpful. If you enjoyed it, please give it a thumbs up, subscribe to the channel, leave a comment, and share it with your friends. Your support means a lot. See you in the next video.